Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on electromagnetic induction from May June 2022, Paper 4, Variant 1. In this question, we will talk about magnetic flux. We will discuss how to define magnetic flux. We will also talk about magnetic flux linkage, and we will discuss how to calculate magnetic flux linkage. After magnetic flux linkage, we will talk about induced EMF, and we will also discuss some other important points about electromagnetic induction. And we will discuss these topics by solving past paper questions. Let's study together. Let's improve together. For question number 6, part A, we need to define magnetic flux. And this question is very common in past papers. Most of the time, they will ask you to define magnetic flux. So you need to understand how to define magnetic flux in a proper way. Let's try to understand how we can define magnetic flux in a right way. We use symbol for magnetic flux. This is phi, and magnetic flux is equal to BA cosine of theta. And theta is the angle between magnetic flux density, and this is the angle between area normal vector. So you need to understand A in this case, this is area normal vector. Area normal vector. So in this case, if you look at this ring, in this case, area normal vector means area that is means the vector that is normal to this area. That vector we call is area normal vector. Vector normal to the area of this lobe. That is area normal vector. So this is area normal vector. In this case, flux will be equal to BA cosine of angle between A and B. Angle in this case is equal to 0 degrees. So simply flux will be equal to B times A. So this is how you can calculate flux for this one. Now let's try to calculate flux for this second case. In this case, you can see area normal vector. So this is the area normal vector. And in this case, this is B. So this one is B. You can see in this case, there is angle between these two, and angle is theta. So flux in this case will be equal to B cosine of theta. Means this is B. We can resolve this one into two components. So this is one component and this one is the second component. And this component is B cosine of theta. And this component is in parallel with area normal vector. So we have B cosine of theta times, you can write down A. Simply you can write down BA cosine of theta. And theta is the angle between A and B. So simply in this case, flux is equal to BA cosine of theta. So you need to understand, you need to take component of magnetic flux density that is parallel to the area normal vector. So this is how we can calculate. So simply we can say flux is equal to product of magnetic flux density and area. And area you need to take, the area, imagine that this one is the loop and this is the flux. So the angle between this B and this plane, angle is 90 degrees. So another way you can say area that is perpendicular to the magnetic field. That area you have to consider. So let me explain to you how you can write down the answer. This is how you can write down your answer. So first point you can say product of magnetic flux density and area, simply BA. So this is BA. And you have to explain in this case area that is perpendicular to the magnetic field. Means if you have, this is the plane, imagine that this is the plane, so this is the area and magnetic flux is this way. So you have to take area that is perpendicular to the magnetic field. So we have to take this area that is perpendicular to the magnetic field. So this is the magnetic field and this is the area, and this area is perpendicular to the magnetic field. So we have to take this area. Otherwise you can say you have to consider the component of magnetic flux density that is in parallel with the area normal vector, as we have discussed in this case. So this is how you can define magnetic flux. This question has 2 marks. First mark is M mark, If you have written product of magnetic flux density and area, you will get 1 mark, and the second mark you will get if you have explained which component of magnetic field you need to consider. You will get the second mark. Simply you can say area that is normal to the magnetic field. You will get the second mark, and that is A mark. For part B, it is given to us a square coil of wire of side length 12 centimeters consists of 8 insulated turns. The coil is stationary in a uniform magnetic field. The plane of the coil is perpendicular to the magnetic field, as shown in figure 6.1. It is also given to us the flux density of the magnetic field varies with time, as shown in figure 6.2. For part 1, we need to determine magnetic flux linkage. Inside the coil at time t is equal to 0.60 seconds. We also need to give a unit with our answer. This question is simply asking us to calculate magnetic flux linkage. Magnetic flux linkage. And magnetic flux linkage is equal to NPA cosine of theta. And theta is the angle between area normal vector, and this is the angle between magnetic flux density. But for this question, it is given to us that plane of the coil is perpendicular to the magnetic field. It simply means that in this case, the angle between B and A angle is equal to 0 degrees. So simply we can say in this case, magnetic flux linkage is equal to NPA because cosine of 0 is equal to 1. So simply we can write down here cosine of 0 is equal to 1. Now simply we need to plug in values here. N is the number of turns. In the question it is given to us there are 8 number of turns. So this is 8. Magnetic flux density we have to calculate at time 0.6. So we can read from the graph magnetic flux density is equal to 400 millitesla. 400 milli. So we have to multiply with 10 to negative 3 in this case. A is the area of the coil. Side length of the coil is given. That was equal to 12 centimeters. So we can say 0.12. We have to calculate area of square, so we have to multiply with 0.12 again. Simply we need to calculate. If we calculate this one, our final answer has to be 0.046, and the unit of magnetic flux linkage or magnetic flux is simply Weber, WP. So this is our final answer, 0.046, and the unit is Weber. So this is how you can answer this question. This question has 3 marks. The first mark you will get if you have written this formula, and this is the C mark. And the second C mark you will get if you have plugged in these values, and the last mark you will get if you have got the right answer, and that mark is answer. For the second part, we need to state how figure 6.2 shows that the electromotive force induced across the terminals between time t is equal to 0 and time t is equal to 0.60 second is constant. Let's try to understand this one with the help of EMF. EMF is equal to N d phi by dt. If we expand flux, we can write down flux is equal to BA. In this case, simply we will write BA because plane of the coil is perpendicular to the magnetic field. So we no need to consider angle in this case because angle is 0. So the cosine of 0 is equal to 1. In this case, area of the coil is constant. So we can take this out. We can say this is NA dB by dt. And dB by dt is equal to gradient of this graph. So simply we can say d by dt, this one is equal to gradient. So simply we can write down in this case induced EMF is equal to NA times gradient, and gradient in this case is constant as this is a straight line. We can say gradient is constant in this case because it's a straight line. It's a straight line. As gradient is constant, it also means that induced EMF is also constant. If gradient is constant, A is constant, N is constant, it means induced EMF is also constant. So simply we need to write down here because it's a straight line graph. So induced EMF is constant. And this question has only 1 mark. If you have written straight line, you will get 1 mark. and this is the P naught. For our third part, we need to calculate the magnitude of E. In order to calculate magnitude of E, we need to understand induced EMF is equal to rate of change of magnetic flux linkage. And we have discussed this point before. So we can simply say this is rate of change of magnetic flux linkage. And rate of change of magnetic flux linkage, we can also write down NA, because A is constant, N is constant, we can just take out. So we can simply write down here. So this is dB by dt. And dB by dt, this is equal to the gradient of this graph. So simply we can plug in values here. N is given to us, that is equal to 8. Area of the coil is 0.12 times 0.12. Now we need to calculate gradient. So we will take this point and we will take this point. So we can write down value of B at time 0.6, that is equal to 400 millitesla. So we have to multiply with 10 to negative 3 minus 0 divided by change in time 0.60 minus 0. Now simply we need to solve this one. If we solve this, we will get 0.046. This is the magnetic flux linkage and the time is 0.6. And our final answer in this case will be equal to 0.077 volts. And this is magnitude of induced EMF. So simply we need to write down here 0.077 volts. This question has 2 marks. The first mark you will get if you have written induced EMF is equal to rate of change of magnetic flux linkage. You will get 1 mark. And the second mark is answer mark. If you have got the right answer, you will get 2 marks. For part C, it is given to us the procedure in B is repeated, but this time the terminals of the coil are connected together. Means these terminals are connected together. For this question, we need to state and explain the effect on the coil of connecting the terminals together during the change of magnetic flux density, as shown in figure 6.2. First of all, let's try to understand what will happen if you place a conductor inside changing magnetic field. Imagine that we have one ring, but this is not a complete ring. And if we place this one inside changing magnetic field, and the magnetic field means the external magnetic field is into the page. For this question, it is given to us that magnetic flux means the magnetic field is increasing with time. In this case, if the ring is not a complete cycle, in this case, only EMF will be induced. But induced current will be equal to 0. Means in this case, no current will flow in this ring if ring is not a complete circle. Now imagine that we have external magnetic field that is still into the page. So we can write down here, we have external magnetic field that is into the page. And this external magnetic field is increasing with time. Means the magnetic flux is changing with time. If we place a complete circle, means a complete ring inside this changing magnetic flux, so there will be induced EMF and also there will be induced current. Now current can flow, but in this case current cannot flow. Now let's try to answer our question. For the question it is given to us, we have a complete square. As you can see here, we have this complete square. So this is the complete square and the terminals are connected now, so it means this is a complete square. And this complete square is inside changing magnetic field, and magnetic field is into the page, and this magnetic field is increasing with time. And that one you can see in the graph it is given, B is increasing with time. So we have external magnetic field that is into the page, and this external magnetic field is increasing with time. So according to Lenz's law, this square will oppose the change in flux. So how it can oppose the change in flux? It will produce its own magnetic field in opposite direction to external magnetic field. So in this case, direction of induced magnetic field has to be out of the page because it has to be opposite to external magnetic field. So current will flow in this square in such a way that it will produce its own magnetic field that is out of the page. Now if the magnetic magnetic field is out of the page, we can find direction of current. So you have to use right hand grip rule. Magnetic field is out of the page, so you have to curl your finger, and your fingers will give you direction of current. So fingers will give you direction of current, and in this case direction of current will be anti-clockwise. So it simply means that current will flow in this way. Current will flow like this. So this is direction of induced current, and we have found direction of induced current by using right hand grip rule. Now in this case you need to understand current is flowing in the coil. As current is flowing in the coil, so simply we can say there is I induced in the coil. I induced in the coil. As there is I induced in the coil, and coil has its own resistance, so it simply means that energy will be dissipated in the coil. It simply means that electrical energy will be converted into thermal energy. So we can say energy will be dissipated. As energy is dissipated, means electrical energy has been converted into thermal energy. Due to thermal energy, temperature of the coil will rise. So we will simply say temperature of coil will rise, mean coil will get hot. And this question has 3 marks, so if you mention these points you will get 3 marks. Means the 1 point you can say I induce. So in this case EMF will cause induced current, and as current will flow in the coil, energy will be dissipated because work has to be done for the flow of current. As energy is dissipated due to thermal energy, means electrical energy is converted into thermal energy, temperature of the coil will rise. So this is one way to answer this question. Later I will explain you another method as well. So let me show you how you can write down a proper answer. This is how you can write down your answer. You can say induced EMF causes current in the coil. So this one has 1 mark. If you have written this one, you will get 1 B mark. And the second mark you will get if you have written current causes dissipation of energy in the resistance of the coil, you will get another B mark. And the last mark you will get if you have mentioned temperature of the coil rises, you will get an other B mark. So this is one way you can explain this question. Let me explain to you the second way based on forces. Now you need to understand, as current will flow in this coil, and this coil is placed inside external magnetic field. So we need to understand motor effect now, mean how forces will act on this coil. First of all, imagine that we have only this piece of wire, and this wire is placed inside external magnetic field. So we can draw our external magnetic field, and we can place this wire inside this external magnetic field. Now you can use your left hand rule and you can find out direction of force on this piece of wire. In this case, magnetic field is into the page and current is flowing upwards, mean is up. So the force on this one will be to the left. So this is direction of force. You can also find direction of force on this side. If you find direction of force on this side, that has to be to the right, because magnetic field is into the page and current is flowing down. This magnetic force is to the right and this magnetic force is to the left. We can also find out direction of force on this side. Now imagine that we have this wire and magnetic field is into the page. So magnetic field is into the page. So magnetic field is into the page and current is flowing to the left. So the force on this wire will be downwards. So this is down. So the force on this one is down. You can also find direction of force on this side of the coil. You will see the force will be up. So in this case, you can see the forces are acting inwards. Why forces are acting on this coil? Because this coil has current and the coil is inside external magnetic field. So there are forces acting on this coil and forces are inwards. So you can say current will be induced in the coil, and then you can say this part you can remove with forces. You can say forces inverse because the coil is inside external magnetic field. So forces on this coil will act inverse. So you can mention this point. Forces inverse, this will be 1 point. And the second point you will get if you mention there will be forces on this coil because this coil has current and the coil is inside external magnetic field. So this will be 1 point. And the second point you can say current carrying coil inside external magnetic field. So we can say current carrying coil inside magnetic field. So we can say inside magnetic field, you will get the second mark. And the third mark you will get if you have written there will be forces acting on this one and these forces are directed inverse. Mean it will try to minimize its area. So it will try to reduce the change in magnetic flux. So this is how we can answer this question. I hope this question is clear to you. If you have any question, please leave your questions in comments and I will be answering as soon as possible. And the next video will be on quantum physics from this paper and that video will be coming very soon. See you in next video. Bye for now.